There we go. And actually, I can kind of see the terminal a little bit. Not very well. Hopefully, that'll be good enough. Well, we'll have to work on that a little bit next time. Okay, yeah.
Could you type something so I can see if I can see what you're doing? That's really hard to see.
It's not in green, whatever what I just typed.
Okay.
The green is only the part. Sorry, 111 got moved down to 240.
Oh.
So anyway, it's there, I guess. Okay, well, I guess we'll call this good. Were you able to read what I actually typed?
Yeah, I could read that just fine.
Okay.
For some reason, the I you wrote looked like FRI.
Okay.
A really fuzzy FRI.
Oh, weird.
It took a moment for my brain to recognize it was I.
Okay, I'll go one more on the font setting then. I ended up changing this all around because we're going to use actual Linux pretty quick here. I don't know why I wrote high last time. Okay. Okay, cool. So this class, let's get the 111 is moved down to 240.
111?
That's right. Okay, so I gave everybody the syllabus, and that kind of explains the general way classes work, I guess. That's what those things do. I went and didn't open it up over here so I can show you the syllabus. The course website's not on Blackboard. If you haven't moved my classes before, you know this is how I do it pretty much all the time. And it's got the URL and the syllabus. So let's see, most of this stuff is pretty typical syllabus stuff. You can see what class we're in and when it is and where my office is. I set the office hours here. As usual, if my door's open, you can feel free to stop by. I only close it if I'm working really hard on something like, lecture prep, or I'm playing a video game and don't want anybody to know it. It looks like I'm hiding in there when I'm in here because I leave the lights on because they're compact fluorescents and it takes forever to warm up. But they actually save energy even when they're left on over lecture time, so I just leave them on. It's my contribution to destroying the environment, I guess. My daughter broke one the other day too, which is also awesome. Anyway, there's the course website up there. If you don't like typing the tilde, you can just go to a software. There's a link on there. This time we'll learn about file systems and that kind of stuff. Oh yeah, you're here for this one. I keep sending everybody out to 111.
So.
Yeah, but you don't have to go to 111. You can stay here. That's fine. You can even have a syllabus. I won't even call you late because you were down my bed at the right room, or the wrong room. No, wrong room. Okay, so a lot of times they divide the operating system kind of into two parts, where you got a kernel, and this takes care of interfacing with hardware and managing memory and that kind of thing. That's what we're going to talk about in this class, 430. You probably already had or had equivalent experience or something 228, which covers the above the kernel area, user land. And we won't talk much about user land in this class. I mean, we'll use it some because we're going to be using the system, but that's not really the focus of the class. So we have to learn about the kernel. This one requires more programming than the other one. So it's numbered 400 something and the other one's numbered 200 something. Because this one you actually get to learn how to write software for the kernel, which is going to be lots of fun. Okay, so one of understanding file systems, how you store files, understand memory management, and device drivers. So device drivers, when you have a computer, you have a variety of hardware in it, and it's not necessarily the same as anybody else's, but the operating system hides all of the diversity at this level and makes it appear exactly the same. And so that's something that the device drivers handle for the most part. If somebody sells you a device, it'll come with something that interfaces between that device and your operating system kernel, and that's called a device driver. It gets matched into the kernel, and if it crashes, and the operating system crashes, which is wonderful. Talk about process scheduling. This is something that's always been an issue with operating systems that handle multitasking. basically who gets the CPU at what time, because there's not very many CPUs in a system compared to how many processes there typically are. And so anyway, scheduling is a big deal. And then finally, boot up. How do you get from sitting there with no power up to running an operating system, which is actually going to take quite a while to cover. Okay, and then at the end, you get to learn how to write Linux kernel modules, which should be lots of fun. Okay, I have a backwards quote here. That's embarrassing. It's probably replicated in print on here, too. Yep. Or, no, it's fine in print. Anyway, so the Art of Linux Kernel Design. This is on the 0.11 version of the Linux kernel, which you might recognize as out of date. I think it's from the early 90s. And it has most of the major systems intact in some sense, and it has a lot less code, and so it'll be fairly easy to understand. The book is much newer than the Linux 0.11 kernel, so the author has his own defense of it. Now, if I recognize the name there as a Chinese name, and in fact, the book was written in China and translated into English later. This is actually kind of the opposite of the way things are normally ending up handled in academia, where English is the first language of books. 111 is actually downstairs if you're looking for that one.
Oh, yeah.
But you can stay here and learn about operating systems if you want to.
That sounds good, but I gotta go.
So the book has funny translation in some parts. That's fine. I looked through it. It's understandable. It'll just look funny and occasionally. Okay. Okay. Normally in English, we sort of get the position where we speak the dominant language in academia, and everybody else just has to adapt to it, which is convenient for us. I remember one conference I was at, it was in Quebec, and there was a lady from France who was trying to explain how her program worked to a gentleman from China, and he didn't speak very good English, and she didn't speak very good English, and they were trying to use it as a medium for communication. Finally, somebody who knew English and French stood up and translated for her into English, and they got that one through. But anyway, so it's just kind of a funny quirk of academia. English ends up getting used as a main language. I don't know why. I guess it's most common. Okay, maybe. Spanish might be. Oh, let's go on to something else. Okay, so grading. You have midterm and a final, and they only total 30%, so theoretically you can pass the class with a C without showing up for either one. I don't recommend it. There's not too much wiggle room that way. But, you know, if you're really super confident and you just don't like tests and you're okay with getting a C when you can have a better grade, then, you know, go for it. Okay, lab assignments. I'll be posting about 7 of these. And so there won't be one every single week. I like to skip the lab on weeks when there's some kind of project that I expect you're spending a lot of time on, or sometimes leading up to the final. I'll just kind of post these as they come. And they'll vary in difficulty. Some of them will be, I'll be like, oh, well, that wasn't very hard. And other ones will be like, so why is this a lab assignment again? Most of the time, the point of the lab assignments is to either prepare you for the projects or to let you get some experience with some topic that I'm not going to dedicate an entire project to. And occasionally there may be scavenger hunts where you just look through the kernel source code and find like 5 examples of something or other. Those are usually easy unless for some reason that day you can't find any examples of whatever it is. So they vary. Okay, projects. The kernel programming project is worth twice as much as the other projects. They'll probably have less than half as much source code, but when you're writing something for an operating system kernel, it ends up being a hassle, and I don't know why yet. And I'll find out when the time comes. But for some reason, it's probably going to be twice as hard. Kernel programming is that way. You'll see. I'll make lots of mistakes up here. We'll figure it out. Well, sometimes, last time I was teaching this course, I get something worked out in my office, and it would work fine on my computer. I bring it up here, and it just like crashes this one 5 times, and eventually it's like, okay, well, we'll resume this one next time. End up debugging it for an hour after class. Okay, so anyway, that one's worth twice as much. The other ones, you don't actually have to write code that goes into the kernel. There will be a memory management simulation, a file system simulation. There'll be one where you play with the memory management on the operating system. And there'll be one where you crash the operating system, or at least get it very stuck using a fork bomb. So those are all kind of more straightforward. They're actually written in user land, although they're designed to illustrate stuff about the kernel. Okay, deadlines. Typically, I don't take late work. I like to be able to grade the assignment as soon as it's due. You normally don't get around to it, but I like to try. And sometimes I get it done. And so anyway, I like to have it all there. And so if you're half done with the project, just turn it in for half credit. I used to have this sliding scale on it where you could turn it in like 3 days late for 30% off. But then you end up doing all the work and then getting a lousy grade anyway. So I don't know, it's bad. Yeah.
Is it all right if we leave the assignments on a soft drive?
Well, some of the assignments you're not allowed to test on my soft drive. But yeah, well, I might actually set up a unified turn-in system where you can turn it in directly from my soft drive. I have it all there. I wrote it one day and then never used it for anything and forgot about it. I'll dig it up, and so you'll be able to turn it in really easily from my soft drive.
Actually, I thought we did use it last semester.
Some people did. I forgot about it, and oh, you're nodding too. Okay, a couple people used it. Maybe it actually works.
Yeah, the command was like turn in your assignment name and then the course number.
Yeah.
Yeah, useful.
Yeah. Anyway, I'll dig that up and make it work. I think I might have to change a couple of numbers in it to turn in stuff for classes this semester, because I think it'll try to turn it in for networks or security. Attendance, I do have to take attendance for the financial aid purposes, and I see that we have 1, 2, 3, 4, 5, 6, 7, 8 people here, and so there's one person who's not here because he had to go to the hospital, and not for him, for his daughter, and there's somebody in Alaska, so I'll assume she's with us in spirit, and so I guess attendance is taken. Good. Done. So you guys can show up or not show up. I'm a little bit concerned that seeing I'm actually making videos of this, everybody will just decide to watch the video at home. We'll see. You can't ask questions if you do that, though. Okay, I think everybody's seen a academic dishonesty policy. In fact, I think I cut and pasted from other syllabi. And basically, when you write a project, write your own project. I need 1 project per student. And when you have a lab, you can work together on them if you want to. Collaboration is allowed on labs. And if somebody asks you a question like, you know, my project isn't working, how does this function work in C again? You know, you can talk to them about that kind of stuff or share ideas. Or so how did you approach this problem? Just don't share your source code with them. That's giving them the answer. That's too far. You know, it's like an English class. You know, if you wrote an essay and your friend wrote an essay and your friend's like, is this argument persuasive or not? You know, you can say, yeah, it is, or no, you should do this. But you can't be like, oh yeah, here's my argument. Go put it in your paper. Okay, so anyway, basically the same there. And so I'll just tell an amusing story about this, because you guys are 400 level, and so we're past all the cheating, and so we can laugh at the freshmen. I had this one class, and I was at the Maryland University, Western Washington University, where I taught for a couple of years. And there was a student, and what did he do? I think he copied test answers off his neighbor. Anyway, I caught him at it and sent him an email, and he never responded. And so eventually the registrar's office tried to contact him, they couldn't, so they just failed him, and I think he was expelled at that point. Later I noticed a student paper laying on the floor, and it had his picture on the front. Apparently he was like a big basketball star. I had no idea. And it was this article about like how wonderful he was and everything, and I'm like, oh, I think I might have just got him kicked off the team. Anyway, it's funny. Okay, there we go. I've never really had problems with 400 level on that stuff, though. Everybody who cheated is gone. Okay, so the calendar. Let's talk about the calendar later. Okay, I'll talk about kernel programming and why different parts of the class a little bit, and we'll get back to the calendar some other day. Okay, so general description of projects. We'll go over that a little more when we talk about the calendar. Okay, I want to answer a question here. Why operating system development in Linux? As in, why not, you know, Windows or OS X or something else? And so there's a few reasons for that. First thing is it's actually the world's most popular operating system now, thanks to Android. And Android uses a pretty close to stock Linux kernel. It has some modifications, but not very much. Mostly it just runs on a phone and has a different user interface on top of it. And so anyway, we get to study the world's most popular operating system, which is, I think it's irrelevant. The other thing is the source code is available for Linux, as in you can just go and download it legitimately from anywhere you want. The syllabus addendum, which is attached to your syllabus, but I didn't cover it because it's attached to all of your syllabi for all of your classes, and if we all covered it, we'd waste lots of time, has like an illegal file sharing policy. And the Windows source code is actually available online if you want to do some illegal file sharing to get it. But obviously we shouldn't be doing that in class, seeing the syllabus says not to. And so we won't go look at it, we won't touch it, but it is out there. It's not really out there in the sense that it has a various explanations of how it works and things, because you can't go publish a textbook that's like, okay, well here's this illegal source code, and we'll go study it. So Linux, you can find a good textbook that actually covers the source code. Not a big deal. So that's another reason for it. Now, those reasons would apply, well, kind of, at least the last one, to the BSD family of operating systems. And actually, when I took a similar class to this as an undergraduate, we studied NetBSD. And NetBSD is open source, so that's great. It's well designed. Some people say it's better designed than Linux, and so it'd be a good candidate too. The reason I shied away from that one, even though I'm actually a little bit more familiar probably with NetBSD than Linux in a kernel sense, is nobody really uses NetBSD. You're not going to see a lot of jobs out there where on the required skills they say they want you to know about NetBSD. And so with Linux, you get a little bit more marketable skill there. Now some companies like, okay, we need a developer for Android kernel because we make smartphones. Yeah, if you say, well, I don't know how to do NetBSD, I mean, you might be like, well, okay, that's another operating system, you can figure it out. But it'd be better if you can just say, well, yeah, I wrote a Linux kernel module before. So that's the reasons behind the choice of Linux for this. We'll talk about other operating systems to some extent with design trade-offs and that kind of thing. There we go. Okay, last time I used the current version of Linux for everything, and actually that's what we'll be writing kernel modules for. But we're going to use Linux 0.11 for examples of stuff. So last time I ended up finding I'd dig through the source code and find these examples, but then I'd have to tell everybody, okay, well, ignore this 300 lines. Let's go pay attention to this a little bit here. Oh, it's extra complicated because of this, which is not really relevant, so we'll ignore that part too. I want to avoid that whole discussion this time as much as I can, and show you source code that's a little simpler. So there we go. That's 5.11. And we'll write software for the current version of Linux, so don't feel like you're getting skills from the 90s. You'll be up to date. That's okay. Just want to cover the principles there. I put NetBSD and Windows 2K. I wanted to mention these are the other operating systems that I've developed modules for. And so I've actually I wrote a device driver for Windows 2000 before. And it's pretty hard, actually, when you can't see the source code. In fact, there's a lot of things where nobody quite knows the way things work except for Microsoft, and they're not telling. At least there were back then. It was 10 years ago I did that. So, I don't know. The class I took as an undergraduate, we developed a device driver for NetBSD, and most of that process was learning about our hardware, which is badly documented, and a lot of stuff was known only to the manufacturer. And the NetBSD part was easy. And in the second half of the course, we wrote the device driver for the same device for Windows 2000. And at that point, we knew how the device worked, but then we were working with an operating system where we didn't know what was going on. I thought about digging up a piece of hardware for this class, but I want to cover operating systems in a little more general sense. So we'll end up just writing some kernel modules, and we'll get some kernel programming, but we won't do actual device driver development. I may show you a device driver at some point. Linux worked pretty okay last time we did the class, and so we'll keep going. Okay, Isoptera. Most of you know this already. Isoptera is my little server that's housed out at the server room. Here's the point on Isoptera. We can't do kernel module development on Isoptera. Isoptera is locked inside a room that I don't have a key for, and I can't have a key for it. And it's kind of a noisy room. It's full of servers and fire suppression equipment and whatnot. So basically, I don't want to crash Isoptera. So, and you don't have admin access to Isoptera anyway, so you guys can't test kernel modules on there even if you wanted to. But we'll test them on the machines in here. These ones dual boot Linux and Windows, and that'll be great. Most of the projects you can run on Isoptera, but not all of them. For example, the fork bomb project fills up the process table on the operating system and makes it not function well anymore. And so you can't do that on Isoptera either. Because if anybody crashes Isoptera, I'm going to have to go down there and get into the room and push the reset button on the front of it. Okay, so you can have access to it. I think everybody here has an account on Isoptera, but that'd be of less utility here. Okay, so as far as what the kernel does, One of the things it does, so when you start up a computer, back when you had DOS, the CPU would run in what's called real mode, where it has where the programs have access to all the resources on the system. Modern CPUs run in protected mode, and so the code that you run when you write a program that runs on an operating system is actually kind of seeing an idealized version of the computer, and it's not allowed to access things like device memory and that kind of stuff. This compartmentalizes it. Makes it hard for a program to actually crash the computer. A program can consume all the computer's resources, make it run really, really slow. But ideally, if you have a program that misbehaves, you can terminate it from the operating system. You can just open up Task Manager or whatever and kill it. And this is because the program is not allowed to access the devices on a computer directly. This is running in protected mode. The operating system gets to run code in real mode, where it can actually access any feature on the CPU or any memory address it wants. So the kernel has to take control of this area between the program and the hardware and manage things. And first thing it manages, file systems. You guys have all wrote a program at some point, I assume, where you accessed a file, right? And when you did it, you didn't have to worry about how the file was stored. You know, you just say you want to go open a file, and then you can start looking through it from the beginning. Well, the operating system has to handle all of that stuff. And so it'll have, it's called a system call that does that sort of thing. So if I go over here and I look at the manual page for read, I'm going to get something. This is from manual section 2, which is system commands. And it says read from a file descriptor. And so you got this system call, which allows you to read information directly from a file. Kind of directly. As directly as the operating system goes. So if we were to look at, say, scanf, you can look for stuff from a file with that. And that's a higher level library function. It'll be on top of this one. This one, if you have a file descriptor for your operating system, you can go ahead and read stuff from it. Incidentally, before we get too far into this, I mentioned manual section 2. Manual section 2 has Linux system call. System call is something where you're going to ask the operating system to do it for you. And it's different from a library, where, say, if you're using the C standard library, where you might use like printf or something like that. There you're asking for a library function, which is going to be implemented in terms of system calls. Here you're calling the system call directly. It's a little less common to want to do that in the program, but they certainly get used. And you can tell what you're looking at in the Linux manual by looking at which section up there. So we're in section 2, that's system calls. So if we go here and man printf, we're going to be looking at, well, this is the wrong printf. This is the one that you get if you type printf. And we want one in section 3, which is going to be part of the C standard library. And you can see its header is an stdio.h. And so that's what we're looking at there. Okay, so the operating system gives you this this call read. And if you look at the other ones, open, there's 2 open. Open, for example, opens or possibly creates a file. This is again something that's in the system calls. Operating system provides all this stuff and makes it happen. And so in the class now we'll go study exactly how it makes it happen. Now, the thing is, when you ask for something like open here, it gives you a couple of parameters. You have a path name, and then you have some flags. And these can be like, you want to open it for read access or write access or append. And so the files, the operating system has to take this path name, which is just a string, and figure out what file you mean by that, and then retrieve the file off of the disk. Well, the disk, okay, it depends what kind of disk you have. If you have a spinning disk, like a magnetic disk, you've got a 3 terabyte drive or something, you got a disk, and then you got an arm that goes out, you got a hole in the center, and this arm can move. So the arm, can go out there or something. You can go anywhere in this region. This is all concentric circles. It's not like a record where it's a spiral. They're actually concentric circles. And so it's divvied up that way, and then it's also divvied up into sectors. And so this head will move around and read a sector. Well, the operating system has to go from your path to which sector do we want to read from. And so there's different ways it does that. We'll talk about the file allocation table at some point for a FAT32 or FAT16 style system. And I'm biasing myself towards this side of the room because I don't think the camera actually shows that board. It shows this one kind of. Okay, so so the file allocation table way this works. So you got all these sectors, right? You just pick some spot on here. Say, okay, this one in here, the center circle. Let's take the center circle like that. Okay, this is going to consist of file names and which other sector they're in. And so if we visualize this kind of in a linear sense, because now it's easier, what you got is this table, and it's got entries. And so, for example, in DOS, where this system was used, the entries allowed you to have a 13-character file name, 8 plus extension. No, it's 11. 11 characters worth of file name. 8 characters of name, and then 3 of extension. So you had all these entries, and so then you'd have some, file. And you actually have to have a little bit more space here. I didn't draw enough. It tells you which sector and track. So we'll have some number. These are called cylinders. These circles. Because actually, I have a stack of platters, and so you can look all the way through it. So you actually have to know which platter to. Anyway, I'll have some kind of numbers here that allow you to figure out where on the drive to look for this file. And then if you see another file, it's the next entry, and so on all the way down. And so then you just got locations these things are stored at. Well, if it's too big to fit in the sector, then you might have like an entry for the rest of it somewhere in here. And you probably are familiar with defrag, because you used to have to run defrag on these file allocation table systems. Defrag happens when you fill up your drive and you delete some files, and you write some more files, and so on. And pretty soon they're all over the place. And so it can't just be like, okay, this file starts here and it's this length, and just start reading. It's going to be like, okay, read a little bit. Okay, where's the rest of it? And so on. And so that's fragmentation. It makes it really slow because it has to skip all over the drive looking for your file. Okay, so that's a simple file system. Now, most people don't use a file allocation table style system for their main hard drive anymore. That's how you probably own one because they're using digital cameras and SD cards and things. And then for your regular file system, Windows NTFS is the current system. Use a system of B trees for we'll cover B tree file systems later. The basic principle is instead of having a table like this, you can do a tree kind of. It's not a binary search because there's more ways than that, but a tree search to find your file, and you don't have to just start at the beginning and look until you find it. For Linux, is I guess the BTRFS is up and coming, B-tree file system. There's also about 4 others. XFS is made by Silicon Graphics. The EXT system was a standard for a lot of years. There's JFS, journaling file system. I think IBM wrote that one. There's RiserFS. We'll talk about that a little bit because it's kind of introduced a lot of novel ideas. It used to be big, but then the guy who wrote it, Hans Reiser, he actually killed his wife, who was instantly named Nina, and he hid her body somewhere, but eventually got caught because there was all this blood in his car and things, and so he's in jail now, and he's not maintaining his file system anymore, and nobody else really understood it, so that happened. She came all the way from Russia to marry him, and I guess it didn't work out, and so he deleted her. All right, RiserFS is kind of disfavored these days. There's actually a later version called Riser 4, which is never actually finished. And people have studied it and looked at stuff in it, adapted it into other file systems. And so the ideas persist despite their source. Anyway, so there's a variety of file systems, and I'm busy lecturing on the open page here, which makes no sense. That doesn't make any sense either. Put that one. Oh yeah. So yeah, FAT Silicon. FAT is a very simple file system, file allocation table. Okay. Oh, memory. So anybody here remember the 4 GB limit?
Yeah.
Yeah, a couple people. Okay. Here's what the 4 GB limit was for everybody who didn't raise their hand, and maybe more elaboration for those of you who did. So the memory in your computer, main memory, it has to have addresses. And the addresses, there's 1 address per byte of memory. And so each byte of memory has its own address. And that means that if you have a 32-bit number, then you can have 2 to the 32nd addresses. And so that's actually quite a few addresses. If we look at, okay, 2 raised to the 32. Okay, that's how many addresses you get. 4.2 billion here. Well, this is enough addresses for 4 gigabytes of memory. And so if you had a computer and you're using 32-bit addressing, and you decide, oh, all my friends have 4 gigabytes of memory, but I want to be cooler than all my friends, so I'm going to buy 8. So you buy your 8 gigabytes of memory and you put it in your computer, but it doesn't have enough addresses for all of it, so you can only see part of it. And it would actually be worse than that, because most of the time people that were pushing the limit on the memory, they also had a video card that was pretty fancy. And if you have a fancy video card, it'll have a bunch of memory on it too. And so if your video card has a gigabyte of memory, well, that all needs addresses. And your network card will have a trivial amount of memory that needs addresses, and same with your sound card and some of the other gadgets. So you'll have less than 3 gigabytes. That's not very good. And the way to fix it is you need more addresses. When I grew up, my address at my house is 4 digits, and when I got older, it eventually turned into 5 digits because there weren't enough around anymore. Here in Idaho, we're going to be getting a new area code soon. You know, we've been 208 for a long time, and people have shirts that say 208 and that kind of stuff on it. They're going to have to add one soon because we're out of addresses. So you just do the same thing with computers. But the thing is, you don't want to add just like one more and have a 33-bit address. That'll work fine for your 8 gigabytes, but then you're just kind of pushing the problem off. So they went to 64. And now you can have that many bytes of memory, which is a lot more. Yeah?
How about something interesting about Bluetooth?
Yeah?
Apparently it's 32-bit and have 6 gigs of RAM instead of 4.
Oh, that's interesting. I don't know how that works.
I don't either, but when I was looking it up over the summer, that's what they were talking about.
Interesting. There was an extended addressing scheme that was going to go to 36 that was around for a while. Maybe it's actually, I thought it was good. It was just, you know, went away when we went to 64, but maybe it persists in some way. But that would be more than 6 gigabytes. Yeah. Oh, anyway, so you double the number of bits, and it's way more than double the amount of bytes. And nobody's hit this yet. Now, I realize that we just pushed the problem off, you know, for the next generation. And, you know, that's fine. I don't know how many bytes that is. A lot. Eventually we'll get there. I mean, back when the 32 bits limit was established, people had like less than a megabyte in their computers. And so it was kind of like, wow, if we ever get 4 gigabytes and have this problem, we're just going to rejoice. And that was his thing. Okay, so anyway, there's this address limit. I didn't quite mean to do that, but that's fine. So virtual memory here. I guess the address limit isn't strictly what I wanted to talk about here, because I got off on a tangent. The memory that you see from your computer program is actually kind of extrapolated from what you have on a computer. So even with a 32-bit system, even if you only had, say, a gigabyte of memory, your program would get a 4 gigabyte address space. And then it could use what part of the address space it wanted to. Now, the operating system has to make this translation here. So the program, you know, you say, okay, I want an array, and I want this array to be a kilobyte in size. And you say that to the operating system, whether you create it with new in C++ or malloc in C or whatever, you know, you just make your array. Just start using it in Python. And no matter which one you've done, you know, you get some memory allocated, and then the operating system figures out what to do in terms of the computer's physical memory, and the addresses will be different. And the operating system doesn't even have to give you physical memory on the computer's main memory that's installed. So if you're running your program, and say you're on a 64-bit system, and the system has 16 gigabytes of main memory, and you ask in your program, okay, I want an array that's 128 gigabytes in size. The operating system may well say, oh, sure, here you go. And then it won't actually allocate any main memory for you. It'll just say, okay, you got it. And if you start using it from your program, it'll start allocating main memory. If it runs out, it'll use the hard drive to store some of the other information. And if it runs out of hard drive and main memory, then that's a problem. It probably won't say okay if it doesn't have enough between the two. But then it also means that the operating system, you know, suppose you got 4 gigabytes of main memory. Let's stick with 8. I won't change numbers. I guess I just did. Okay, so suppose you got 8 gigabytes of main memory. You got 2 programs running, and you say, okay, I want an array, and I want it to be 8 gigabytes, because we're going to go load some DVDs off the hard drive. Okay, so then program 1, goes ahead and loads this DVD, and the operating system might shove all that in the main memory. And then suppose you pause the movie, and you go away for 3 days, and then you come back, and you start running the other DVD player, with the other one paused in the background or minimized, or maybe you forgot about it or something, or don't want you to lose your place. Well, when the second program starts using memory, the operating system will take the stuff that the first program had in main memory, squirrel it away on a hard drive somewhere, and start using the main memory for the second program. And then if you go click on the second program on taskbar, your hard drive light's going to come on for a while. It'll move stuff back into main memory for that program, but the program is none the wiser. And the only thing is it ran really slow. Other than that, I just in a program at some point they probably said, array at this index, we're going to take that and do something with it, and that line took forever because it was on the hard drive. But that's fine. So the operating system has to deal with this whole thing of keeping the addresses straight from one to the other. And yeah, let's see how that works. I'm just talking about the problems today. We won't solve any of them. Okay, so input and output. That's another thing where you do a lot of stuff. So in your in your programming things, you just say like print something. You don't say how to do it, and you don't say anything about the screen resolution or any of that kind of stuff. You just say go ahead and do it. It gets done. The operating system has to deal with that. And so this note about hardware-independent programming. So if you're writing something in C, you say printf, or C++, you use cout, whatever. It has to call an operating system. It has to do a system call at some point. And if you're using a function in your programming language's standard library, then it'll call a system call, such as write, and end up putting stuff on the screen. So this is one place where device drivers come in, because everybody's screen and video card, okay, not everybody, some people may have the same one. A lot of people's ones are different. And so then the device driver has to take care of abstracting all this stuff and get stuff to come out on the screen. Okay. There tend to be subsystems inside the kernel. So, for example, on the keyboards, you can have a keyboard that uses USB or one that uses PS2. The USB system on a computer is actually a polling style interface. And so your USB port will periodically ask each gadget attached to it, do you have anything to say right now? And then that gadget will either say, yeah, I need to communicate this, or no, I don't. And so my keyboard here that I have, this is an IBM Model M. It's from 1994. And I keep this here in order to defend all of you, because if the terrorists come in, I'll chuck this at them and they'll all die. It's pretty heavy. It's got a big metal plate in it. Anyway, it uses a PS2 interface, and I have it plugged into this this gadget here that PS2 in one end, USB in the other. And so what this gadget has to do is, when the operating system asks it, do you have anything to send right now, if I push the keystrokes, or push the keys, since it was last asked, it sends them to the operating system. Now the older interface, the one this keyboard natively supports, PS2, it works completely differently. If I have that plugged in with a regular PS2 port, there's not one on that machine, so I can't do it. Some of those over there are PS2 ports. It will actually interrupt whatever the CPU is doing every time you push a key. So you push a key, generates an interrupt, whatever the CPU is doing gets stopped. The CPU has to deal with that keystroke, and then it can get back to doing whatever it was doing. So as you can imagine, that actually does require a certain amount of CPU time, but it also gives you a quicker response. Mice are the same thing. You have a PS2 mouse, which interrupts the CPU every time the mouse is it gets moved at all. And or you can have a USB mouse, where the mouse will store up whatever input it's got to say until it's asked for it. Sometimes gamers prefer PS2 mice because they say they can see the lag on a USB mouse. They're probably nuts. The polling time is very, very short. but there's people that have a definite opinion here. So anyway, they work differently though. Okay, so you got two different ways that hardware is managed there. And at some point they have to get merged together, because it's ridiculous to process the keyboard twice in completely independent streams. And so there's a USB input subsystem, which is going to talk to the keyboard input. And then there's a PS2 interface subsystem for the keyboard, which handles the interrupts and things and gives the keys to, again, the same keyboard interface sort of functions, and they get processed off together. Okay. I have anything more to say about that? Not really. Maybe one note. Last time for the kernel module programming, I haven't decided if we're doing the same thing this time or not. Last time I taught this class, we made a keylogger, and the logger actually worked on a PS2 subsystem, and whenever an interrupt was generated for the keyboard, it actually took the key that was generated and squirreled it away somewhere. So you install this keylogger Linux kernel module, and put it on a machine, and then when anything is typed on the keyboard, it would be recorded, assuming you're using a PS2 keyboard. We didn't support the USB system when we did it last time. I don't know what we're going to do for kernel module programming this time. We might do that. We might do something else. Everybody thought it was kind of fun that time, but I don't know. I guess I'm kind of tired of that project. We'll see. If I think it's something that's more fun, we'll switch to that. Otherwise, we'll just do the same thing again. The other problem with that is only some of the computers in this room have PS2 ports. And so it worked basically on this bank of computers over here. Oh, that one looks different. It probably isn't. That's an AMD one. It worked on any of the Intel machines in the room. And we had to go find some PS2 keyboards, because the ones sitting here on the desk are actually USB. And I don't know. It worked okay. We got more people this time, I think. I don't know. We'll see. Okay, so that's input and output. Processes and scheduling. This one, oh yeah, let me show you this. Okay, so we're on the software here, right? Okay. If I go ahead and hit top, this shows me the top processes in terms of CPU consumption. And looks like I'm running something that's using 1.3%. Oh, Oracle and Tomcat are using stuff. Those are database management systems. And you can see Oracle's actually running 4 processes, and it's occasionally doing things. I don't think anybody's using it right now. Tomcat is something to do with web servers, and some folks wanted it on there for some project or other, and so I installed it. I don't know anything about it. Yeah, you can see Oracle's doing it. I'm using some resources on a few different things. You can see user over there. So there's a number of processes on here that are running, and you can see it changes which one's using CPU and that kind of thing. Okay, now if we look at the computer CPUs, CPU info. You can see we got processors, and they're numbered. There's processor 41, 45. I think I skipped by a few. Yeah, there was 43, 44. 40, anyway, my scroller is pretty fast here. Numbered up to 47, 0 to 47. So it's got 48 processors, 0 to 47, to manage. And so what the operating system has to do is go from that list of processes to matching processes with actual processors when they need to do some work. And so that's the task of the process scheduler. Now, it says 48 processors on a soft thread. It's actually only got 24, but they're hyper-threaded, so they appear as 2 to the operating system. But that's what it's got to manage. If you look at, some computers will have less than that to manage. If I go home for a minute, that's taking a moment. There we go. I'm actually uploading electron or microscope images from my home computer to a software to show them to my CS101 class pretty soon. Okay, I want to SSH again. This is my home computer, but it has a few processors. Pi at 192.168.0.100. Okay, this is a computer that's out in my chicken coop. It opens and closes a door every morning. That is its purpose in life. Eventually, I wanted to use a webcam to take a picture of the chickens every time it does it and send them to me. But anyway, that's all it does. Okay. We'll take a look at its CPU info. As you can see, it's got a few less resources to deal with. It's got one processor, which is numbered 0, and it's an ARM processor. BogoMIPS, this is how BogoMIPS is like an approximation of how powerful a processor is, and it scores 2.00 BogoMIPS. Is to a good score. Well, let's scroll up and see what a software's processor scored in terms of BogoMIPS. 4,801. And it's an approximate figure in terms of performance. It's not exact. But the basic idea here is the process scheduler on the Pi here has a lot less to work with in terms of resources. And if we look at the processes that are running on the Pi, it will have quite a few. And hey, it actually showed me the command of all of these. YCD there that just popped up to the top, that's the management for the wireless interface, which we're actually going through. It's not connected to a physical wire, it's on wireless. My chicken coop doesn't have a wire. I'd like to put one out there so I can put a backup device out there. But anyway, so you can see the wireless card's using some. This display here top is actually drawn a full percent of the CPU. On the software is negligible. I don't think it made the chart, but on here it keeps popping up there as like something. And so the operating system has to deal with that. And you notice that we're actually kind of doing two things at once here. Like we're displaying this, so you can see it's updating. So obviously we're using a wireless interface for communication. And that's taking some CPU time, we can see it. But generating this thing, that's taking some CPU time as well. And so we only got one processor here, and so the operating system is taking care of using this one processor to manage all of this stuff and keeping it going here. I showed you this one because on a software, you know, there's not even really 48 lines on the display. You can be like, oh, well, that's simple. We'll just give each one its own CPU. Well, not so here. So there's okay, and there's more that go beyond. This is just like the top processes. There's more. If we do PSAXU, we'll get a list of all the processes on the system, and if we take that and run it into word count, it's a little slow my interface there. Looks like 81 processes. Word count gives you lines, words, characters. So let's see, lines. I don't care if you know how to do that or not. But 81 processes running on the Pi. I hit Control D, which closes the connection there. I'll hit it again. Most of the reason we're so slow here is actually not the Pi's fault at all. I've got my home computer uploading all these 20-something gigabytes of stuff over my home internet connection, which is a cable 1 connection out at the end of the orchards, and so that's why it looks sluggish. Like the Raspberry Pi is slow, but that's not why it's doing this. And I'm kind of just I don't know about this not logging out business. Okay. Well, that's the process scheduler. I wanted to get back to my notes, so maybe I'll just pull them up on the website here. Still got lots of time. They're all posted. Okay, now they're in the super light font. Okay, so there we go. The other issue in here is some programs might want more than one processor. That happens. That's how multi-threading works. That's how you take advantage of a modern CPU because they usually got more than one core. And I'll talk about that a little bit. Okay, time sharing is obviously what we're doing on the Pi. There's this operating system called DOS. Anybody here use it? I used to use it. One person. Man, every year that goes down. Okay, well, if it was 1989 and you were buying a personal computer, you'd probably buy one with DOS, unless you had the $20,000 back then to spend on a Unix workstation. 20 to 100, somewhere in that range. Anyway, and it's called Disk Operating System. But people question then and now whether or not it was actually an operating system or whether that was marketing speak. Here's why it's a disk operating system. When you bought a PC clone in the 80s, it would come with 2 floppy drives designated A and B. You'd put your operating system disk into drive A and turn on the computer. Then the computer would boot up and it would load the operating system into memory. Then you would take the disk out of the computer and it would keep running. It would be fine. It would be in main memory. And you put your program disk into drive A. If the program had to save data, that disk would go into drive B. And then you would start your program. And so the program data that it needed would be loaded off of this disk. And obviously it couldn't replace the operating system in main memory. That just wouldn't work right. But the program could load itself into main memory, and you could use data storage on its disk if it needed to store something like your word processing document. And and off you go. And that's how your computer would run. They were pretty good. If you were, kind of wealthy, you'd go buy a hard drive. And a hard drive was numbered C, not B. And a lot of times you had to take out drive B to put in your hard drive because you needed space in the chassis. It wasn't required. I mean, if you had space, you could keep them going. Anyway, so that's how disk operating system would operate. Now, mention that you put your program disk into drive A. A lot of programs have this hard coding. If you put the disk into drive B, it wouldn't work. So you might ask, well, where do you put your other program? You know, if you're going to run your, your web browser to look at Facebook, and you're going to run your word processor at the same time. Well, the answer is you didn't, because it would only run one program at once. So you'd finish what you were doing, and then you'd get out of the program, and you'd take out the disk, and you'd put in the next program's disk. And so it lacked this multitasking feature of running two things at once. And a lot of times that's included in the definition of what an operating system does. So I put these things up here as challenges operating systems have to handle. And a lot of times when if you look up like operating system on Wikipedia, it's kind of expected that it handles shared memory, it handles multitasking, it'll handle process management, it'll handle your networking for you. Now these are kind of what people expect from an operating system, and DOS didn't deliver in that case. The other thing in DOS was memory. So I mentioned protected mode, DOS didn't have protected mode. If your program said it wanted to store something into memory address such and such, you could just go ahead and do it. It didn't matter if there was a critical system function happening at that address or not. You say, oh, hey, I want to go store this here. And so there was absolutely no protection in that regard. And so if your program crashed, you would turn your computer off, and then you take out the program disk, and you put the DOS disk back in, and you turn the computer back on. That worked. And in fact, some programs didn't have a way to get out of the programs. I used to play this game when I was young, Space Invaders, and the implementation of Space Invaders I had, even if you had it on a hard drive or something, you couldn't get out of the game. There was just no way to do that. So when you're done playing your game, you would turn the computer off and then on again. Anyway, so DOS didn't necessarily meet the definition of operating system in a modern sense. Obviously, it was named Disk Operating System, so Microsoft at least considered it an operating system, or wanted you to. But it's kind of gone by the wayside. Networking. So operating systems usually manage network access, and it's kind of expected that you're not going to have to install something special to get on the network these days. We'll talk about network access maybe a little bit, but we have a class for networks, CS435, so we're not going to dwell on networks too heavily. I just put it there to kind of complete the list of stuff that people expect from modern operating systems. Okay, so other issues. You want some kind of security usually in operating systems. DOS, as I mentioned, didn't have any security. So typically in an operating system, you want to make it so one program can't retrieve data from other programs, or crash your computer, or upload all your data to a server in Bolivia. There's certain things you want your operating system to maybe handle, but a lot of those things aren't really built into the operating system, and so a lot of times you end up with a userland program to handle a lot of the security function. That said, there's a lot you can do inside the operating system. For example, on a Unix-style system, the principle is that one user shouldn't be able to affect another. So if you have one user on the system, except by using resources. So if you have some user on the system and they're like, okay, well, I'm going to go connect to my friend's account and take all their bank passwords that they stole and steal them. They're stolen after that. The friend didn't steal them. There's his bank passwords that he put on the system. And I change all of his programs around and turn his desktop funny colors, and I shouldn't be able to do that. So that's a security from one person to another. And so the way this sort of thing is implemented is using permissions, typically file permissions. And this seems pretty stuck here. I'm just going to Alt F4 it. And I don't know where Putty went. I'll have to get Putty back. That's downloads from here. Downloaded it somewhere. Oh, never mind. I just explained the system. You guys know about permissions. I'll cover that later. I put security on here twice. I don't know why. A loader is sometimes a category that DOS is put into. A loader is something that takes a program, loads it in memory, and starts running. Operating system still has to do that, obviously, but that's not all it does. That was kind of all DOS did, in a way. I guess it managed your file system for you. Yeah, I did that. Okay, so user space, so I won't spend too much time on that, just user interface stuff. Oh, I do want to show you /proc. Okay, I'll get Putty back. Okay, it's somewhere around on my file system. If I lean over here and push WinR, :. Okay, this is drive D. Putty's not there apparently. Oh, ThawSpace. Hey, I probably put it there. Okay. Oh, That's right, all the fonts and things are different. Okay, so we're connected. General consensus among my classes has been that black and white is hard to see. So I will change that to whatever the other thing is, white on black. I just did it wrong. So I'll change that. I never like these little interruptions in class. Any questions so far? I can answer while clicking.
Do you have a general comment about Windows 10?
I have never used Windows 10.
Okay.
As a matter of fact, I also haven't used Windows 8 or 7 or Vista. I used XP as a Windows software developer for a while, and I used Windows 2000. That's the most recent one that's ever been installed on a system that I owned. And I use Windows 98 a fair bit. So if you want me to compare 98 to 2000 for you, I can do that. No, the only operating system I use is Linux. And I have a Mac laptop that I bought at a garage sale for $25 because I was hoping I could load some software onto one of the kids' things that they've since quit using. But I had too old of operating system versions, so I couldn't do it anyway. That's the last time I tried to use a different operating system. Oh, and of course, right now I'm running this from some version of Windows. I have done that before. You use some computer. Not like, oh, I'm not going to use this until it runs Linux. I'll use my wife's iPhone occasionally for something. I know how to check the weather on it. So I've used iOS too. It's very user-friendly, I guess. I don't know how to do anything on it. Oh yeah, /proc. /proc is a special file system. So file systems, you typically give it some kind of file name. You're like, okay, here's my file, and it gives you back the file. And most of the time, that file is stored on a hard drive, right? You're like, I want /such and such, and it's on a hard drive. Well, the proc file system is special. These aren't real files. I think I showed you CPU info. Let's show you a different one. So if we print out this file called uptime, it gives me these numbers here, which mean very little to me. But what's happened here is I asked to read the file. The Linux kernel took this request and it gave me that without actually consulting the hard drive at all. And that in some way represents the amount of time that the computer's been on, like since last restart. There's actually a program called Uptime, which will take that and generate this much more intelligible output that says it's been up for 42 days and 1 minute. But it got that from that uptime file up there. That's probably like how many seconds it's been on or something like that. And I don't know, maybe like seconds and I don't know, something. Some small unit, because there's a lot of them. Anyway, so the proc file system has stuff like this. Things where instead of a real file, it's actually giving you something it gives you some kind of information on what's going on in the system. And I will show you how to make files in this /proc file system from your Linux kernel module, where when you query them, it will run a function in your kernel module, and you can say whatever you want the function to return to present as the contents of the file. And actually, the devices, they have the same thing. Okay, so this is the /dev directory, and this is files that represent gadgets that are attached to the computer. Now, I wish I was connected to, I was in Linux on this machine here, because I would start printing out the output of the file that represents the mouse and then go move it. And you see a whole bunch of gobbledygook appear on the screen. But I'm connected to a software, which, as mentioned, is in a room that's locked somewhere else, and in fact doesn't have a keyboard or mouse attached to it. So that's slightly less interesting. I can't do the other one either, which is to put stuff into the file that represents the sound card and have it make funny noises. So anyway, these things represent files on here, and these files represent gadgets that are attached to the computer. File descriptor in bad state. Well, apparently that one doesn't like to be printed out. Oh, anyway, the SDA, whatever ones up here, like SDA, SDA1, etc., these represent hard drives. And as a matter of fact, if you want to duplicate your hard drive, you can take this file and copy it somewhere else, and you'll get the whole hard drive, just kind of as a whole stream of things. It's a little bit of an unintelligible stream, but if you copy absolutely verbatim to something else, and then tell your operating system, hey, look, I got a file system of this type on this other thing you copied it to, you can actually start using it. Like you can duplicate it that way. And so if you bought a new hard drive and you want to duplicate your existing file system onto it, you can actually do it with these things. Incidentally, if we go ahead and replace the contents of that file with like a 0 or something, it might get rid of the hard drive, or it might everything on the hard drive, or it might refuse. I don't know. If they're nice to people, it would refuse. But there's no guarantee, because see, it could be a really neat feature. Because if you had two hard drives, and one was like, you just put this one in, and it's identical to the other one, and you want to make a backup, it would make a lot of sense to just copy the device from one to the other one, and get the whole output from the hard drive from one to the next. And so it might actually be allowed. This is part of the reason why you typically don't run around as administrator. See, I'm logged in here as Seth, which is my regular user, the same as all of you. And so I try to change one of these files in here as Seth. In some cases, it might let me, but if it's important, it's going to tell me to go take a hike. And that's what I want, because that way I can't accidentally do it. There's a friend of mine, and he was somewhere in his device tree, and he typed in rm-rf ... because he forgot where he was. He thought he was, buried like such and such deep, but he actually wasn't. If I type that right here, ... is the previous directory, like outside of dev, which is /, which is the root of the entire file tree in Linux. And so I would be saying, remove recursively everything, and -f means don't even ask me about it. I'll just do it. And he was logged in as an administrator. And as it happened, the machine he was logged into was our ACM student club, our file server, or it wasn't a file server, it was just our general ACM server that we all pitched in money to buy. He was a little embarrassed the next day. It took a while to get it all set up again. It didn't delete everything. I mean, at some point it hit something important, and everything ground to a halt. But anyway, but if I run this like this, do it. Okay. Sorry, I was it refused. Good. And even if I do rm-rf everything here. Oh, whoa. Okay. I started seeing permission denied there, and I was like, wait a minute. Good. I forgot that it was going to continue to try to remove every file. In which case, I would have killed all of my own files. So I saw that coming, and I was like, wait a minute, I know what's going on here. But luckily, it didn't get to home Seth and start trying stuff there. And luckily, nobody has me allowed to write to their home directories. As well, you shouldn't. By default, I don't have permission to write to anybody's directory. I have admin access. I could just become admin and do it, I guess. But yeah. Okay. So what was I talking about? Oh yeah, file systems. I got sidetracked by talking about admin privileges. So there's special file systems on here, and for kernel modules, you can make entries into these things, special files. When somebody tries to modify it, it calls a function inside your kernel module. Kernel modules are really not that unusual. It's just a bit of C code. It's not like a program where you have a function called main. It's just these functions, and they have to be named the right thing and all that kind of stuff. And then you mash them into the kernel, and when certain things happen, your functions get called with certain parameters. And then it just runs your code inside it. It's not that magical. There's a few things that are funny about kernel C programming, and so actually we're going to spend the first 3 weeks of the semester learning how kernel C code works. One of the things is there are certain tips and tricks that you use regularly in kernel C programming that you don't really use in application development. So, GoTo. Anybody here use GoTo recently in a program? Raise your hand if you use GoTo ever.
Whatever.
Okay. Use it in my 250 class?
I did.
Yeah, I like to show people GoTo. It's used in kernel C programming. Okay, so even if you know how to program in C and C++, except for Brian, nobody here has used GoTo. Well, GoTo is all over the place in the kernel. So I'll explain how to use GoTo. So that's what the first 3 weeks are going to be, learning C programming stuff that you don't necessarily use outside the kernel. And I'll show you actual kernel modules. Here's the other thing that you use a lot. How many people here use a structure, a C struct, that is full of function pointers? You have?
Yeah, I did something screwy in one of my 250 projects like that.
Oh, okay. Oh, for my class again.
Yeah.
Awesome. Okay. So except for Gus, nobody here has done that. Okay. So we'll cover that too, stuff like that. And it's actually really fun because I get to go talk about esoteric programming techniques that I don't get to mention in CS 111. Sometimes I mention them just because I can't stand not to, but nobody cares. So this will be fun. I get to show you all the secret arts. Let's go back to the course calendar because I did want to explain that at some point. And I said I'd come back to it. I was excited about talking about other stuff. Okay. I kind of like teaching this class. I like teaching it this, I'm liking this semester because I have like classes I'm excited about, and I don't teach anything else this semester. Next semester is different. Really fun with online. Okay, so this is kind of an introduction to old operating system today. So what I'm hoping that you come away with is a new appreciation for all the things your operating system does for you. Now you can be like, wow, this helps me so much every day. When you pay $100 to get the next version of OS X, you'll be like, wow, thanks to Apple for doing this. Only $100. It handles the mapping between the memory that my programs see and the physical memory on a computer.
It's free now. That's Windows.
Is it free? Seriously?
Yeah.
Windows is the only one left that costs money?
Actually, Windows 10 upgrade, if you have 7 or 8, is free. Granted, you technically, if you do that, you don't have support from them. You'll still get updates or whatnot, but you can't say, there's a problem here, fix it.
Okay.
You void that right unless you have a business license and you advocate for one.
So they're slowly and steadily getting dragged into the black hole of free. Understand. Okay, good for them. Well, kind of. A lot of you might want to go work for them and make a bazillion dollars at the end of this. So I shouldn't say that. They actually make most of their money on Office, Microsoft. Microsoft Office is their top cash cow. Windows is like way back from that. Okay, and their Office suite may eventually get dragged into the black hole of free too, but they won't let that happen for a long time. If
They might
help it.
eventually make a new one from Mac too.
Yeah.
Seriously, the day.
Well, I do know that their newest one for Windows is now, you can either do a monthly or a yearly subscription, and if you do so many, you do get it technically for free, and it's their last one, so you get rolling updates. So as updates come, you can get them, I think.
Interesting. Yeah, they're not going to let that one go if they can help it. I think the whole company will get dragged in the black hole of free before they let that one go. Oh yeah, so introduction to operating systems. So you should have know what it does. And so in kernel C programming, we'll start talking about that on Thursday, and that'll be exciting. Okay, and then so after that, more stuff that's in kernel C programming. I mean, pointers. You guys have probably covered pointers in some class, right? We'll go nuts with the pointers. We'll make pointers to functions, pointers to structures that are full of pointers to structures that are full of pointers to functions. It'll be fun. There'll be a lot of stars and ampersands involved. And so yeah, that'll be great. Okay, C conventions, how that works. So dynamic memory management, C, because that gets important. If you make a memory management mistake in the kernel, you can make a memory leak in the kernel. And that's going to make everything happen in a delightful manner. Labor Day doesn't really affect us, so I left on my calendar, I guess, for the sake of completeness. So we're talking about like binary, bitwise ands and that kind of stuff, which will be a review from 250, but it'll get important in a minute, so we'll cover it, not in a minute, in like 4 weeks. Module interfaces and looking at a sample module. I've got Linux kernel modules around, I can show you examples. Okay, we'll talk about file systems a little bit in terms of how they work and how a B-tree file system works. The main goal of this week here is to explain A, what does a file system do, how does it work, and B, to explain why is a B-tree file system something you want on your computer and why you already have one there. And so anyway, I'm just hoping to answer those 2 questions in detail. I'll just assign a couple of Wikipedia articles for that. Our book doesn't really seem to cover file system design that well. My master's degree was actually in file systems, and so it's a topic that I rather enjoy. So that's why it's the only one that gets like a special online reading and things. So then after that, we'll get started on our book. And so at this point, you'll know how to do kernel C programming. And so all the kernel C programs in the book should hopefully make some degree of sense. And so we'll cover that whole thing from one to the next kind of topic. The book doesn't necessarily name the chapters after their main topic. In fact, the book's kind of organized mostly in terms of the boot up process for the first 5 chapters and then specific topics after that. And so you notice files kind of come back at some point. That's fine. Files are a really big deal in Unix type file system, and you use them all kinds of different ways. So I have topics that I want to talk about, and I just kind of matched them up with the book as best I could, and I hope that ends up working out for us. So you know, I do want to explain to you, you know, for example, how these shells work. And so chapter 4 of the book seems to be that's when shells are established during the boot up process. Seems to be the most relevant point to go on a little bit of a tangent about shells. So we'll do that. And you know, 228, you'll learn how to use a shell. Here we'll talk about a little bit about how one works. A shell isn't user land, so it's not like really a topic for the course, but I think it's kind of a good thing to understand too. So, yeah, flip 11. Okay, and let's see, yeah, etc. Okay, I put the due dates on the projects there. I haven't posted the actual projects yet. I'll probably post project 1 before next time. I actually have it written. I have project 2 written too. I'm going to mostly recycle those ones. Some of the other ones are going to have to change a little bit, so I'm not going to post them right away because I'm reluctant to commit on those. But I'll probably get the first 2 posted this week, so you can see what you're in for in the beginning at least. And well, what else? So yeah, this is kind of wrap up thing. Topics of interest. You know, if you have something that you really want to talk about, you can suggest it. Last time I taught this course, cloud computing was suggested. I think I talked about it a little bit, but I was teaching networks the next semester, so I was a little uninspired to go into depth. Because, you know, it seemed like a more appropriate thing for networks. So, you know, if you really want something in there, I can do it. Now, I've talked about including Android coverage. And you notice there's no, like, Android week on here. I want to just kind of work Android in. Android's close enough. I think we can just kind of, you know, when we talk about stuff, be like, oh yeah, and here's the, here's how it's done the same way in Android. I kind of want to find an actual little Android gadget, and we can write a kernel module for it, because I think that'd be fun. Let's see if we get to that or not. If not, we'll just show you it's basically the same thing. That'll be fine too. But it would be sort of cool to do that. The other thing is, it looks like they probably have to be jailbroken in order to change the kernel on an Android phone. And that's certainly possible. Yeah?
On Android, it's overrooting.
Yeah.
And it's legal, unlike with iOS.
Yeah, it is. It has possible technical hiccups. You know, like you get the one gadget where the procedure online doesn't work or whatever. And if you're dedicated to solving the problem, you can do it. I'm just always reluctant to introduce projects that can have technical hiccups because then everybody gets stuck on that instead of things that I actually want them to focus on. We'll see.
Yeah, that's why I was glad my phone was the version it was. Otherwise, I could have had some major hiccups.
Yeah, yeah, exactly. But we'll see. It may work into the module project. I might also end up with an optional module project, like you need to write the keylogger or write something for Android or something like that. I'll make an announcement in 6 weeks about it. If I haven't by then, remind me because I forgot. Any questions about the class or how it operates? We're pretty much at the end of time here, and I have to go teach another course in 15 minutes. So, well, I don't have to go anywhere. It's right here. But I do have to recover my voice for a moment because it's feeling scratchy. And so I guess I'll be all done. Start recording.